Alright kids, I'm going to be real with you, and I completely forgot that this lesson existed. I did not plan on assigning this today, but here it is. Lesson 11-7, Graphing Rational Functions. Alright, another graphing lesson. Another graphing lesson. Alright, you know what? I'm going to do my best to make this as easy as possible. Alright, because really graphing rational functions, at least the way that I need you guys to understand it right now, does not need to be that difficult. It does not. All right. I'm going to try to make this as easy as possible. We're actually going to start off with a really easy first part of the lesson. All right. All right. So away we go. All right. Easy part of the lesson is we are going to talk about how to find the excluded value for each function. Now, this is super easy. There's actually only two steps that we need to follow in order to find the excluded value. Now, the excluded value will always have to do with the denominator. All right, so all we're going to do is take the denominator. In this case, the denominator is x minus 2. And we're going to set it equal to 0. We're going to say the denominator is equal to 0. And then you just solve for x. I add 2 on both sides. So the excluded value equals 2. All right, for the first part of your homework, that's all you're going to be doing. Is finding what we're going to call the excluded values. We have talked about excluded values before, but this is a little bit of a recap. And today we're going to find out, well, what to do. Why do we even find these excluded values? What's the deal with excluded values? All right, so same thing. Part B, we're going to go ahead and find the excluded values by setting my denominator equal to 0. In this case, my denominator is x plus 8 is equal to 0. And if I subtract 8 on both sides, x is equal to negative 8. So that means that when the excluded value equals x is equal to negative 8. All right, easy enough? We can go ahead and do this one for funsies. All right, what's the excluded value for this function? Well, x plus 7 is equal to 0. I subtract 7 on both sides, and I get x is equal to negative 7. That is the excluded value. Now let me go ahead and try to explain why do we call it an excluded value. Right? Okay, so what would happen if I plugged in negative 7 into this function? Y is equal to 3 over x plus 7. Well, if I tried to plug this in, I would get 3 over negative 7 plus 7, which is equal to 3 over 0. So go ahead and type that into a calculator. Maybe you already know this because we have talked about this before, but what does 3 divided by 0 equal? Undefined. Alright, this is undefined. Now, why? We're not allowed to equal by 0. That's a no-no. That is illegal in the realms of math. So why did we even do this to begin with? Okay, so what we're going to figure out is when we graph this value of 0, because our denominator is not allowed to equal to 0, it cannot equal to 0, all right? There is no point of the graph when I graph it there at x equals negative 7. There's nothing there. Don't believe me? Well, maybe you'll believe my good friend Desmos. Hey, yo, Desmos, where are you at? Here I am, dog. All right, here we go. So this is Desmos.com, and I went ahead and I typed in our functions. This is the got it question that we were just doing. Y is equal to 3 over x plus 7. Now, I want to remind you, just guide you towards this point, that this is going to be a shape that we haven't seen before. So far, let's just do a recap of shapes that we have seen before. So far, we have seen stuff like y is equal to x plus 2. And this is a regular x, so it's going to be a linear function. All right? Then we talked about stuff like quadratic functions, which make parabolas. We talked about cubic functions, which make snakes. All right? We have stuff like, maybe we'll use stuff like the absolute value, which makes a V shape. All right? We've talked about square root functions. Right? We'll just I messed up. I'm trying to type this in as I go. square root functions that look like that. We've talked about exponential functions, which maybe will have something like the variable is in the exponent, right, where it makes a skateboard ramp. All right, we've talked about all these different shapes, but we haven't seen anything like this yet. So I'm going to go ahead and click this button. We're going to see what this looks like, and we're going to call these shapes rational functions. We're going to call these boomerangs. All right, so now we have the boomerang shape. Now notice there are two of them. And this looks very different than what we're used to seeing. We're used to seeing one continuous graph, or starting at one point we can trace the line, but this thing looks a little different. All right, so here's the best way that I've been able to explain it so far. How many of you guys have seen or played the game Pac-Man? All right, the video game Pac-Man. All right, now I remember back in my day when I was a youngin', one of my favorite places to go with my parents, and still to this day, one of my favorite places to eat is a place called Frantone's. And Frantone's in Norwalk actually had like a little Pac-Man table. You sit and play. And I like Pac-Man. I was not good at Pac-Man. I always lost at Pac-Man, but I played anyways for the love of the game. And when you play Pac-Man, what happens when you go off the edge of the screen? Well, if you're Pac-Man and you're going and you're trying to go towards the edge of the screen, when you're playing Pac-Man and you go and you go off the edge, you end up back on the other side of the screen, and there you go. All right, so in this case right here, this function is, I do call it the boomerang shapes because they look like two boomerangs that are pointing to each other. But this is actually following like the Pac-Man rule. It starts on one side and it goes down off the edge of the screen, and then it comes back on the other side and it just continues its motion. So technically this is going, is going to the right, and then it continues over. Now, interesting enough that we were just talking about exclusions. All right, we said that when we graph this function, we said that x is not allowed to exist at -7. And this is a line for -7. And what's happening? Is there an x part of that graph? Actually, no. What would happen if I typed in a line, x is equal to -7? Well, guess what? It makes an interesting shape, all right, or it kind of proves the point that there is no value of x, a real value of x that exists right here. Actually, let's go ahead and change the way that this looks. We should make this a dotted line. All right, because this value for x equals 7 is a word called an asymptote. Asymptote. All right. This is a special line that graphs approach, but they typically do not touch. All right. So as this line goes, as this graph, as x gets bigger, it approaches this line, but it doesn't touch. And it goes down to -infinity, and then it comes back, and then it reconnects here. Interesting, right? Maybe. I don't know. All right. So this line, this excluded line, so that's why we call it an exclusion, because it's not included in this graph. It's not included in the red graph. All right. This line, this is what we're going to call a vertical asymptote. The vertical asymptote, a line going straight up and down, is not going to exist here. All right, so when we talk about exclusions, what we really mean is find the vertical asymptote. Okay? Interesting enough. All right, so far I think I got your attention with the Pac-Man, with the noise and everything. It's true. I don't know, maybe the creators of Pac-Man, maybe they got the idea of going off the edge of the screen and continuing back from the other side from graphing rational functions. I don't know. All right, so hopefully, there he goes. Back on the other side. All of that just to prove my point. Okay, so now that we've seen Pac-Man in action, we realize, okay, what this function is doing is going down one side and coming up the other side. I want to ask about this boomerang shape. Now notice these two boomerangs, they point to each other, and they are in two different quadrants. If I think of this dividing line, this vertical asymptote, all all right, as one dividing line. And we can say that this line right here at y equals 0, this is another dividing line. Let's go ahead and put that here. Y is equal to 0. And we'll go ahead and call this, another purple dividing line just to make it look like that. Notice they're in different quadrants. All right, and what I will point out to you is that positive functions like this one, this is a positive function, will always be in the upper right and bottom left-hand quadrant across from each other. We would think of this normally if we had the 4 quadrants, quadrant 1, 2, 3, and 4, they're always going to be in 1 and 3. If I had a negative function, like either a negative sign in front of the whole thing, notice they flip in the opposite quadrants. All right, the asymptotes didn't change, all right, but positive is in 1 and 3, and negative is in 2 and 4. All right, so that's something I'm going to try to make this lesson as easy as possible, at least when it comes to graphing. Now let's go ahead and look at problem number 2, and they're asking what is the vertical asymptote of this graph. So in order to find the vertical asymptote, all we're going to do is take the denominator, x plus 2, and set it equal to 0. So that means if I subtract 2 on both sides, x is equal to negative 2. That means that at negative 2 we have a vertical asymptote. All right, that's the first thing. Then they want us to graph the function. Now, if they don't say anything else, we're going to assume that the horizontal asymptote is going to be at 0. And the reason we're going to do that is because the horizontal asymptote, the line that's going left or right, is going to be whatever is added at the end. All right, so you find the vertical asymptote, all right, the VA, by setting the denominator equal to 0, and the horizontal asymptote is going to be at the end. We have the va and the ha. Now, this is a positive function, so that means that we are going to have boomerangs in quadrants 1 and 3. And that's all I need from you guys right now. Like, I don't need you guys to have super exact ones. There are ways you can always make a table and plot values for x and y. But at least at this level, Algebra 1, I'd rather you guys get the shapes and the quadrants right. If you can tell me where the vertical asymptote is, and the next example, the horizontal asymptote, and you can correctly identify what quadrants they're supposed to be in, you guys will be in good shape. So let's look at got it question number 2 and see if we can graph this. What is the vertical asymptote? All right, so the vertical asymptote of this graph, function h of x is equal, so we're just going to go ahead and take the denominator, x minus 6 is equal to 0. If I add 6 on both sides, x is equal to 6. So that means the vertical asymptote is x is equal to 6. That means we're going to have a up and down line, dashed line, here on 6. Now the horizontal asymptote, there's nothing added at the end, and we'll go over that in problem 3 to kind of go over that more. So that means that our horizontal asymptote is going to be at y is equal to 0 because there's nothing added at the end. And I notice that this is a negative function, so instead of being in quadrants 1 and 3, it's going to be in quadrants 2 and 4. And notice that these lines, these boomerangs, they never touch our asymptotes, they only approach it. So this brings us to the very last thing that we're supposed to talk about, is how to identify all asymptotes, whether they're vertical or horizontal. So if we ever have a vertical asymptote, it's going to be whatever is in the denominator, the opposite sign of the denominator, set the denominator equal to 0, and anything added at the end is going to move our function up or down. This should be very, very similar to what we talked about before. Like notice, let's look at this example. This example is saying, what are the asymptotes of this guy right here? Well, the denominator is going to say x is equal to 1. So we have a vertical asymptote at 1. And this thing moved down 2. Down 2. And because it's positive, it's in quadrants 1 and 3. Let's use Desmos to help us graph this guy right here. Now I notice that I have my denominator is going to be equal to negative 3. So I have a line there. My thing moved down 4, so I have another line there. When I graph it, they are in quadrants 2 and 4 because it's negative.